Hello and welcome to the second part of the Devlog series for the Irregular Engine. This time we're going to look a little into the mathematics behind the lighting and shading models. What you can see here is the calculation for a material model which is quite commonly used actually. I use this model in the Irregular Engine, but it is also used, for example, in Blender's Eevee or other engines. These calculations model the most common behaviors of light. To illustrate this, I'm going to switch to Blender for a second. As Blender principled material is pretty close to the material setup I use in the Irregular Engine. First of all, to understand what these calculations mean, one has to understand that in PBR or in light calculations in general, we distinguish two different types of reflection. The first is diffuse reflection and the second is specular reflection. The specular reflection then again is separated into two different kinds. The first is Fresnel reflection, which you can see here. And the second is conductive reflection or metallic reflection, which you can see here. What you have to understand is that specular reflection do not tint with the albedo color of the material. So even though the material surface is green, the color of the reflection is not green. This is not the case with conductive materials. They tint the color of the light itself and thus they look a little different. Also, Fresnel reflections have the property that they get stronger at low viewing angles. So you can see that in the upper part of the sphere here, it is almost a perfect mirror. In fact, it is actually a perfect mirror. If we zoom in a little, you can see that here right on the edge, it actually reflects perfectly every light that is incoming in there. In Blender, the Fresnel reflection is controlled with the specular slider here. The specular slider essentially is a remapped value for IOR, or index of refraction. The Fresnel term depends on the index of refraction of the first and the second medium. Usually the air is modeled as vacuum or just air, which has an index of refraction of 1, which means it can usually be omitted. Actually, to be exact, conductive materials are Fresnel as well. The issue with conductive materials is that they have an imaginary IOR. And as you can probably guess, it is quite difficult to deal with imaginary calculations on the GPU in parallel. Thus, usually the Fresnel effect is not physically modeled in most metallic workflows. But in Blender recently they changed the priority of reflection. So if you actually have a metallic material and add a specular value to this material setup, you can see that now on the edge you see the Fresnel reflection. So you can model this kind of reflections as well. So let's see how this works in mathematics. First of all, we have A, which is the albedo color of the surface. Then we have the metallic value M, which is also given. Then we have the absolute specular color. Absolute specular in this case means that this is the specular which we would get if the surface was a perfect mirror, or to put it a little more precise, if it reflected 100% of the light as a conductor with a albedo of 1. This is the absolute specular. Then we also have D, the absolute diffuse. Same game again. Absolute diffuse means what would the reflected light be if the surface was a perfect diffuse surface with an albedo of 1. Then we also have the absolute conductive value, which is just the absolute specular value multiplied with the albedo. This is to get the green tint of the light. Then we have FR, which is the Fresnel reflection, which we get from the Fresnel equations. We're going to get to these later. Then we have the Fresnel transmission, which is just 1 minus the Fresnel value. Then we have F for the outgoing Fresnel part, D for the outgoing diffuse part, and C for the outgoing conductive part. For these three, we essentially only factor in the Fresnel and metallic values in a way that it mixes properly together. Then the outgoing light will essentially just be the diffuse plus the Fresnel plus the conductive part. If we then just put in the terms for the variables, we get this quite heavy looking term here, but actually it can be rewritten in a quite neat way. First of all, we can see that we here have a product with 1 minus m, and here we have a product with just m, which means we can rewrite this as a mix function, which means we mix a times d over pi with this c here by m, and as both of these products multiply with ft here and here, we can just factor that out in front of the mix function. Then in the next step, we rewrite ft as 1 minus fr, which we get from up there. And also we rewrite c as s times a, and now again both terms multiply with a, thus we can factor out the a in front of the mix function. Now again we have 1 minus fr and fr, which means we can rewrite this as a mix function again, which leads us to our final term. Here we mix the diffuse and the specular part by the metallic value, multiply that with the albedo, and this then we mix with the specular by the Fresnel. And this essentially is how you get this kind of material setup here. And this is the same way that the lighting and material model is going to work in the Irregular Engine. Okay, let's take a look into the Fresnel equations. You can see those are quite complicated. Usually in real-time rendering, the so-called Schlick approximation is used, but I thought I could also just use the full term if I rewrite this a little. You can find these equations as they are on Wikipedia, somewhere here. But as you can see, those are quite heavy to compute and we want to simplify them. First of all, the Fresnel effect is polarization dependent, which is why we get two different equations for two different perpendicular polarizations of the light. In rendering, usually we do not care about polarization, thus we just take the average of both of them. So now in order to be able to actually use these equations, we gotta rewrite and simplify them a little, as those are way too overkill to being used as they are on a GPU. If we scroll down a little, we can see the first approximations we are gonna do is we are gonna assume N1 to be 1, which is the IOR of vacuum or air. And N2 is rewritten as N, which is the IOR of the surface material. This is just to simplify the notation. Then we have this N here, which is the surface unit normal vector, and we have V, which is the view unit vector from the point to the camera. The first thing we are going to try is to factor out terms that are constant throughout these terms in general. The first thing that we see is cosine theta, which is just the dot product of n and v. We are going to call this w. Then we have s, which is short for the square root part, which simplifies quite a bit by replacing the n1 from here with 1 from the IOR of vacuum, but that still is quite a heavy term. Also, here we use the sine of theta, but we do not have the sine of theta, we only have the cosine of theta, and thus we should rewrite the sine as something else, which we can by writing it as the square root of 1 minus cosine theta squared. Also, we wrote it in a way that it's now above the n2, and the n2 now is rewritten as just n. If we apply the power of 2 here, we then get our final square root term, which is the square root of 1 minus w squared over n squared. I hope it makes sense where all the variables are coming from, but this way we could simplify this quite a bit. Now, with w and s being set, this very ugly looking equation simplify to just these two terms here, and then we can use the average as usual. And by having done this, we now have quite accurate Fernel with not too much computation. One more thing I want to talk about is the specular probability distribution function approximation for analytic Lambertian emitters using signed angular distance fields, which is a tiny set of mathematics I came up with to calculate the specular appearance of arbitrarily shaped Lambertian emitters. Actually, this part of the mathematics is the only part which is not physically based. Actually, this more kind of conceptual model, which is inspired by Phong, which I changed and extended in a way that it can now handle arbitrary Lambertian emitters as light sources for the specular term. The only thing this mathematical model needs is the roughness parameter R0, which is given in a range between 0 and 1. I usually get that from a roughness texture. Then S is the signed angular distance to the projected light source on the point's unit hemisphere. Then we have a roughness helper parameter, which is just the roughness remapped to the range from 0 to 1 to 0 to pi over 2. Then we have A, which is the area of the light source projected on the point's unit's hemisphere. We have F, which is a factor for decreasing probability due to a bigger roughness area than light area. And then we have the final probability, which is F times half the cosine of S plus R2 divided to R0 plus a half. And this will be in range of 0 and F. If that doesn't make any sense, I have a tiny visualization of how this function looks. And here you can see, depending on signed angular distance on the x-axis you will get a different probability and thus a different specular strength. You can see as the A value decreases, the probability decreases as well. This is because a smaller light source obviously is less likely to be hit by a reflection ray. So that's it for today's video. I hope the things that I explained today made somewhat sense. If you have any questions and are honestly interested in the mathematics and I didn't explain anything properly, feel free to ask questions in the comments. I will try to answer them as good as possible. If not, I hope you could learn something, and we'll see next time.